Welcome back. This is the final episode of Binomial Coefficients. So I've covered all the main content that I wanted to, and now I'm just going to go through some final examples that show off some more proofs with counting and with the binomial theorem. So let's start with this one. You're running a tournament with 40 teams. There is a group stage where you divide the teams into 8 groups of 5, and each team plays the other teams in their group once. This is called a single round robin. How many group stage games are there in total? Okay, well, the number of games. Well, each group has the same number of games, right? So this is just the number of games per group times the number of groups. But each game is really just a pairing of 2 teams, right? So the number of games is just the number of pairs of 5 teams, right? And the number of groups is just 8. And how many pairs are there from 5 teams that you can make? Well, just 5 choose 2, right? From the 5 teams, you choose 2 to be in the pair. And multiply that by 8. Okay. And, okay, we can just run through the calculation here. 5 choose 2 is 5 factorial over 3 factorial 2 factorial times 8 again, right? This is just 5 times 4 times 3 factorial over 3 factorial times 2 factorial is just 2 times 8. Okay. Cancel the 3's. And we're left with 20 over 2, so 10 times 8, which is 80. So there's 80 games in this group stage. Okay. On to the next one. This is another one of those find the pattern in Pascal's triangle. This time I'm saying that in any row, the sum of the even index entries is the same as the sum of the odd index entries. I think this is best illustrated with an example. Take this row, for example. I'm going to circle these ones as the even ones in green and the odd ones in blue. Now let's sum them. So I have 1 plus 15 plus 15 plus 1 is 32. But at the same time, 6 plus 20 plus 6 is also 32, right? And this is true for every row. You can check it. But why should this be true? Well, first let's phrase the problem a bit better. What is this really saying? Well, what do we want to show? We want to show, essentially, what are the even index entries here? Just n choose 0 plus n choose 2, so on, right? And the odd ones are n choose 1 plus n choose 3, and so on. Note, I'm not writing the end of this sum. That doesn't mean it's an infinite sum. I just mean I don't know whether n is even or odd. So I'm just going to write the dots since I don't know when the sum ends, right? So how do we show this? Well, we use the binomial theorem, actually. So let's take 0. Let's rewrite it as 0 to the n, which is the same as negative 1 plus 1 to the n. Look at that. This is the binomial theorem, right? This is the sum from k equals 0 to n of n choose k minus 1 to the k, 1 to the n minus k, right? Okay, but writing this out, what does this actually become? This is n choose 0 minus 1 to the 0 plus n choose 1 minus 1 to the 1 plus so on, right? But then from the odd and even powers of minus 1, we get this sort of alternating behavior, right? Where we get n choose 0 minus n choose 1 plus n choose 2 minus so on, right? And now we can just rearrange, and then on the left-hand side, we just get all the odd ones, right? We get n choose 1 plus n choose 3, and so on. And on the right-hand side, we get all the even ones, n choose 0 and n choose 2, and all of those, right? This is what we wanted to prove. Okay, that's a nice proof using the binomial theorem. Oftentimes, the binomial theorem is a great shortcut for a lot of these proofs with binomial coefficients. So this next example involves some calculus. If you don't know calculus, don't worry at all. It's far from mandatory. But if you do, I think it's a cool example of how calculus can show up in a lot of unexpected places. So remember we had this corollary of the binomial theorem, that x plus 1 to the n is the sum from k equals 0 to n of n choose k x to the k, right? And if you want to rederive this, you just plug in y equals 1 into the binomial theorem. So writing this out, I think, will make it a little more clear what I'm about to do. This is just n choose 0 plus n choose 1 x plus n choose 2 x squared, so on, plus n choose n x to the n. But now we have two sides of this equation that are equal, so we can just take the derivative of both sides, right? And what do we get? On the left-hand side, we get n x plus 1 to the n minus 1. Notice that this is starting to look a lot more like the equation that we're trying to prove. And on the right-hand side, what do we get? Well, we just differentiate term by term. The derivative of n choose 0 is just 0, because it's a constant. Then for the other ones, we get n choose 1 plus 2 n choose 2 x, and so on. Same pattern, n choose n x to the n minus 1. Okay, this looks so close to our formula. All we have to do now is just plug in x equals 1, right? And then on the left-hand side, with x equals 1, we just get n times 2 to the n minus 1. And on the right-hand side, we get n choose 1 plus 2 n choose 2, so on, up to n choose n. Okay. And, we can add back in the 0 term now. Since it's just 0, 0 n choose 0 plus 1 n choose 1 plus 2 n choose 2, and so on, up to n choose n. And this is exactly what we wanted to prove, right? This is exactly the sum from k equals 0 to n of k n choose k. Okay. So if you didn't know calculus, don't worry about that. But I think it's a cool example of how oftentimes in the world of math, where we're dealing with very discrete, finite things like binomial coefficients, we sometimes find that calculus is very useful, right? Okay. Last example. This one's pretty useful, I think. Specifically when you have binomial coefficients that have this kind of like sum form to them. This formula tells you that you can always break them down like this. Okay, so how do we arrive at this? Well, what is q plus r choose n? Well, what do we know? This is just the number of ways to pick n things from q plus r things, right? But now we can kind of break this up. How? Well, it's a number of ways to pick 0 things from q things and n things from r things. Okay, that's one thing you can do. Plus, so a number of ways, I'll say, to pick 1 from q and n minus 1 from r, right? Because we're still picking n things in total. Plus, okay, you can also pick 2 from q and n minus 2 from r, and so on, right? Up to picking n from q and 0 from r, right? So we kind of break it up in this way. But now what is this? In how many ways can you pick 0 things from q things and n things from r things? That's just, well, I'll just phrase this as q choose 0, r choose n. Our next term, well, we pick 1 from q and we pick n minus 1 from r, right? So when we do q choose 2, r choose n minus 2, and so on, up to picking all n from q and none from r. But then, just writing this in summation notation, this is literally the sum from k equals 0 to n of q choose k, r choose n minus k. And scrolling back up, this is exactly what we wanted to prove, right? Okay, so this is another example of a counting proof. In general, with binomial coefficients, these are the two ways to prove things most of the time, is using some kind of counting argument, or you can use the binomial theorem, right? This is what makes binomial coefficients so nice to work with, I think, is that you have this great combinatorial interpretation, this interpretation in terms of counting, and that provides you a lot of insight, but they're also really useful to just manipulate algebraically to get where you want to go, right? Okay, thank you so much for following along this series. I've had a lot of fun. I hope you learned something, and I'll see you with whatever I make next. Have a good one.